Hello everyone, this is an audio lecture for visually impaired student of physical chemistry of Arts from Rakesh, Bhardwaj, BSc first year. The chapter is Electrochemistry Introduction. In 1800, Nicholson and Carlisle, using Volta's primitive battery as a source, showed that an electric current could decompose water into oxygen and hydrogen. This was surely one of the most significant experiments in the history of chemistry, to show that atoms of hydrogen and oxygen are associated with positive and negative electric charge, which must be the source of binding force between them. By 1812, Swedish chemist Bhardwaj proposed that all atoms are electrified and hydrogen oxygen are associated with the positive and negative charges, which must be the source of the binding force between them. By 1812, Swedish chemist Bhardwaj proposed all the atoms are electrified. Meanwhile, the use of electricity as a means of carrying out chemical chains continued to play a central role in the development of chemistry. Humphrey Davy prepared the first elemental sodium of hydrolysis of a sodium hydroxide melt. It was left to Davy's former assistant Michael Faraday to show that there is a direct relation between the amount of electric charge passed through the solution and the quantity of electrolysis product. Electrolytic and metallic conduction. Substances which allow electricity to pass through them are known as conductor, whereas substances which do not allow electricity to pass through are known as insulator. Conductor are divided into two classes: metallic or electronic conductor. Conductors which transfer electric current by transfer of electron without transfer of any matter are known as metallic or electronic conductors. Metals such as copper, silver, aluminum, etc., non-metal like carbon and various alloys belong to this class. These materials contain electrons which are relatively free to move. The passage of current through these materials has no observable effect other than rise in their temperature. Electrolytic conductors. Conductors like aqueous solution of acid, base and salt, in which the flow of electric current is accompanied by chemical decomposition, are known as electrolytic conductors. The substances whose aqueous solution allow the passage of electric current and are chemically decomposed are termed of electrolytes. The substances whose aqueous solution do not conduct electric current are called non-electrolytes. Solution of cane sugar, glycerin, alcohol, etc. are examples of non-electrolytes. In order to pass the current through an electrolytic conductor, two rods or plates are always needed, which are connected with the terminal of battery. These rods or plates are known as electrodes. The electrodes through which the current enters the electrolytic solution is called anode, which the current leaves the electrolytic solution is called cathode. The electrolytic solution conducts electricity not by virtue of flow of electrons as in metallic conductor, but as a result of movement of charged particle ion toward the respective opposite charge to get electrodes. When these ions reach the boundary between a metallic and electrolytic conductor, electrons are being either attached or removed from the ion. Removal of electron is termed oxidation, which occurs at anode, while addition of electron is called reduction, that takes place at cathode. Hence, flow of electrons through the outer circuit from anode to cathode across the boundary is accompanied by oxidation and reduction. Electrolytes are further classified into two main categories, are as strong electrolytes and weak electrolytes. Strong electrolytes are substances like strong acid, HCl, HNO3, H2SO4, etc., strong bases, example NaOH, KOH, etc., and most of inorganic salts. These indicates almost completely in the aqueous solution or in the molten state and hence conduct electricity. Weak electrolytes are substances like weak acid, CH3COH, HCN, S2CO3, S3PO4, etc., and weak bases NH4OH. These have low degree of dissociation and hence conduct electricity, are known as non-electrolytes. Difference between metallic conductors and electrical conductors. Metallic conductors, flow of electricity takes place without the decomposition of substance. Electrolytic conductor, flow of electricity takes place accompanied by decomposition of substance. Metallic conductor, flow of electricity is due to the flow of electron of ions only there is no flow of matter. The conductance depends upon the structure and density of metal and the number of valence electrons per atom. Electrolytic conductors, flow of electricity is due to the movement of ion and hence there is flow of matter. Metallic conductor, the electrical conduction decreases with increase of temperature. This is because canals start vibrating, which produce hindrance in the flow of electrons. Electrolytic conductors, the electrical conductors increase with increase of temperature. This is generally due to increase in dissociation or decrease in the interionic attraction. The resistance offered by metal is also due to vibrating canals. Electrolytic conductors, the resistance shown by the electrolytic solution is due to factors like interionic attraction, viscosity of solvent, etc. Factor affecting electrolytic conduction. The conductance of the solution of an electrolyte depend upon the following factors. Nature of electrolyte. Strong electrolyte ionize almost completely in the solution and hence conduct electricity to a large extent, whereas weak electrolytes ionize to a small extent and hence conduct electricity also a small extent. Nature of solvent. Electrolytes ionize more in polar solvent, hence greater is the polarity of solvent, greater is the ionization and hence greater is the conduction. Concentration of solution. Higher the concentration of solution, less is the conduction. This is because in a weak electrolyte the ionization is less, whereas in strong electrolyte the interionic attraction are high at a higher concentration. With dilution of conduction increases. Temperature. On increasing the temperature, the dissociation increases and hence the conduction increases. Viscosity of solvent, which depend upon the solvent-solvent interactions. Solvent of ion, which depend upon the interaction between the ion of solute and the molecule of solvent and hence are called solute-solvent interactions. Interionic attraction, which depend upon the interaction between the ions of solute and hence are called solute-solute interaction. Electrical resistance and conductance. Every substance offers resistance to the flow of electricity to small or large extents. The law that gives the exact value of resistance is known as Ohm's law. It states that if the applied voltage V and current I flows through the end of conductors, then resistance R of the conductors is given by V upon I. Current is generally measured in ampere, whereas voltage in volts. If 1 ampere current flows through a conductor and voltage of 1 volt is applied to it, the resistance of the conductor is taken as 1 ohm. So R is equal to V upon I. In the term SI unit, ohm is equal to kilojoule per meter square, kilojoule meter square per Siemens square ampere cube. It is seen that like metallic conductor, solution of all electrolytes also obey Ohm's law. It is obvious that substance which offer greater resistance will allow less electricity to flow through it. This result also flows from Ohm's law, according to which I directly proportional to 1 upon R. The reciprocal of electrical resistance is called the conductance. It is usually represented by C. Thus, C is equal to 1 upon R. It is commonly practiced to speak of the conductance of solution rather than its resistance. Unit. The unit of conductance are Siemens or reciprocal ohms, written as ohm inverse. For example, if solution has resistance of 10 ohm, it is said to have a conductance of 1 upon 10 ohm inverse. Specific, equivalent and molar conductivities. Now, specific conductance or conductivity. The resistance of any conductor varies directly as its length and inversely as its cross-sectional area A. So, R directly proportional to L upon A, or R is equal to rho L by A, where rho is called the specific resistance. If L is equal to 1 cm and A is equal to 1 cm square, then R is equal to rho. The specific resistance is thus defined as the resistance of 1 cm cube of a conductor. The reciprocal of specific resistance is termed in the specific conductance, or is it's the conductors of 1 cm cube of conductor. When an electrolyte solution is diluted, its specific conductance decreases because number of ion current carriers present per unit volume decreases. It is denoted by symbol K. Thus, K is equal to 1 upon rho, where K is kappa. Specific conductance is called conductivity. Now, rho is equal to A by L into R, or specific conductance is equal to conductance into cell constant. Now, specific conductivity. Specific conductivity of a solution is defined as the conductance of a solution of 1 cm length having 1 cm square as the area of cross section. Alternatively, it may be defined as the conductance of an centimeter cube of solution of electrolyte, or in term of SI unit, it depends as the conductor of 1 meter cube of conductors. If the volume of solution is V centimeter cube, the specific conductivity of such solution at this dilution V is written as kV. Similarly, at concentration C, it is represented as Kc. Resistivity R is equal to rho L by A. Ohms meter is SI unit. Specific conductivity is equal to 1 upon rho. Simon meter inverse in term of SI unit is unit. Now, equivalent conductance. One of the factors on which the conductance of an electrolytic solution depends is the concentration of solution. In order to obtain comparable result for different electrolytes, it is necessary to take equivalent conductivities. Equivalent conductance is defined as the conductance of all the ions produced by 1 gram of equivalent of an electrolyte in a given solution. It is denoted by lambda. To understand the meaning of equivalent conductance, imagine a rectangular throw with two opposite sides made of metallic conductor exactly 1 cm apart. If 1 cm cube solution containing 1 gram equivalent of an electrolyte is placed in the container and conductance is measured. According to definitions, conductance is equal to specific conductance K, or is equal to equivalent conductance lambda. If the solution is diluted to say, the conductance of the solution will be the same, but specific conductance become 1 upon 9 as it contains 9 cubes. The conductance is also equal to the equivalent conductance because the solution still has 1 equivalent gram of electrolyte. This is shown thus: equivalent conductance is equal to lambda is equal to 9 into K. In general, lambda E is equal to K into V, where V is the volume in milliliter containing 1 gram equivalent of the electrolyte. In case if the concentration of solution is gram centimeter gram equivalent per liter, then the volume containing 1 gram of equivalent of the electrolyte will be 1000 upon C. So equivalent conductance is equal to lambda is equal to K into 1000 upon C, means concentration. So lambda E is equal to K into 1000 upon N. The unit of equivalent conductance is ohm inverse centimeter square equivalent inverse. Now, molar conductance. The molar conductance of an electrolyte solution is defined as the conductance of all the ions produced by ionization of 1 gram mole of electrolyte. It is denoted by lambda m. Mathematically, it may be defined as lambda m is equal to K into V, where V is the volume of electrolyte solution containing 1 gram mole of electrolyte. Let molarity of solution be m. V is equal to 1000 upon m. From equation first second, lambda m is equal to K into 1000 upon m. Its unit are ohm inverse centimeter square mole inverse. The SI unit of molar conductance is equal to Simon meter inverse liter per mole. The general SI unit of molar conductance is Simon meter square mole inverse. Measurement of electrolytic conductance, specific conductivity, equivalent conductivity, and molar conductivity. Now, electrolytic conductance. Conductance is the reciprocal of resistance. Hence, the conductance can be obtained by the measurement of resistance, and the latter can be found by the principle of Wheatstone-Bridge method shown in figure. It consists of 4 arms containing the resistance R1, R2, R3, and R4. R1 is a variable resistance and R2 is the unknown resistance. When the null point is obtained, there is no deflection in the galvanometer G. So, R1 by R2 is equal to R3 by R4. Knowing the values of R1, R3, and R4 and R2 can be calculated. In finding the resistance of solution of an electrolyte, a reciprocal type, a special type of cell has to be used such that solution is present between two electrodes. The cell thus used is called conductivity cell. It is made up of Pyrex glass and has two platinum electrodes at a fixed distance apart, shown in right hand side. The most serious problem in the measurement of resistance and hence the conductance of solution of an electrolyte is that if direct current is used, it causes electrolysis of the solution. As a result, the concentration of electrolyte near the electrodes change, and this results in the change in resistance of solution. These effects are called polarization effect. To overcome this problem, an alternating current in the audio frequency range of 550 to 5000 cycles per second is used. However, when the alternating current is used, ordinary galvanometer fail to detect the null point, hence the galvanometer is replaced by earphones. Factor affecting conductance, molar or equivalent. The movement of ion gives rise to electrolytic conduction. Electrolytic conduction depends upon the mobility of ion, and anything that inhibits the motions of ion causes resistance to current flow. There are a number of factors that influence the conductance of an electrolytic solution. Intrionic attraction, solvation of ion, viscosity of solution, number of speed of ions, and temperature. Temperature, the average kinetic energy of solute ion increase as the temperature is increases, and therefore the resistance of electrolytic conductor decreases as the temperature is raised. Nature of electrolyte, the conductance depends on the number of ion. A solution which contains larger number of ion compared to another solution of same concentration at same temperature has more conducting power and is said to be a stronger electrolyte. The process of splitting of molecule into ions to electrolytic is called ionization. The fraction of total molecule present in solution as ion is known as degree of ionization or degree of dissociation. It is denoted by alpha. Alpha is equal to number of molecule dissociation into ions divided by total number of molecules. Degree of ionization of an electrolyte in solution depend upon following factors. Nature of solute. Nature of solute. When the ionizable part of the molecule of substance are held more by covalent bonding than the electrovalent bonding, less ions are furnished in solution. Such substances are termed weak electrolyte. H2S, HCN, NH4OH are example of in this class. NaCl, BaNO32, KOH etc. are strong electrolytes in which the transfer of electrons seems to be more or less complete, furnished ion immediately when dissolved. Nature of solvent. The main function of solvent is to weaken the electrostatic force of attraction between two ions and separated them. The force of attraction holding the ions together in any medium is expressed as F is equal to K1 K2 divided by Kr square, where K is dielectric constant of medium. Now dilution. The extent of ionization of electrolyte is inversely proportional to the concentration of its solution. Thus degree of ionization increase with increase of dilution of solution, decrease the concentration of solution. Temperature. The degree of ionization increase with increase of temperature. This is due to the fact that at higher temperature molecular speed is increased, which overcome the force of attraction between the ions. Variation of molar conductivity with concentration for strong and weak electrolytes. As already mentioned in the beginning of this section, there are two types of electrolytes, namely strong electrolyte and weak electrolytes. The variation of molar conductance with concentration for each of these electrolytes is briefly discussed below. Conductance behavior of strong electrolytes. The molar conductivity of strong electrolytes is found to vary with concentration according to the equation lambda concentration m is equal to lambda naught m minus b root c, where b is constant depending upon the type of electrolyte, the nature of the solvent and temperature, and lambda naught m is the molar conductivity at infinite dilution called limiting molar conductivity. This equation is called Debye-Huckel-Onsager equation and is found to hold good at low concentration. Thus, if lambda m is plotted against root c, a linear graph is obtained for low concentration, but it is not linear for higher concentration as shown in figure. Further, the curve obtained for a strong electrolyte shows that there is a small increase in conductance with dilution. This is because a strong electrolyte is completely dissociated in solution, and so the number of ions remains constant. At higher concentrations, the greater inner ionic attraction retards the motion of ions, and therefore the conductance falls with increasing concentrations. With the decreased concentration with dilution, the ions are far apart, and therefore the intra-ionic attraction decreases, due to which conductance increases with dilution and approaches a maximum limiting value at infinite dilution destination designated as lambda naught m or lambda infinity m. Conductance behavior of weak electrolytes. As a weak electrolyte dissociate to a much lesser extent as compared to a strong electrolyte. Therefore, the conductance of a weak electrolyte is much lower than that of strong electrolyte at the same concentration. This is shown in figure, in which acetic acid has been taken as an example of a weak electrolyte. Further, the curve obtained for a weak electrolyte shows that there is a very large increase in conductance with dilution, especially near infinite dilution. This is because as the concentration of weak electrolyte is reduced, more of its ionize. Thus, increase in conductance with decrease in concentration is due to increase in number of ions in the solution. However, it does not reach a limiting value. Further, from the plot shown in figure, it is observed that the plot for a strong electrolyte because linear near high dilutions and thus can be exploited to zero concentration to get the value of molar conductivity at infinite dilution, lambda naught m. However, for a weak electrolyte such as extrapolation is not possible, as clear from the plot for acetic acid. Experimentally also, it is not possible to determine the lambda naught m value for peak electrolyte, as it does not approach a limiting value. The problem was finally solved by Collards, who put forward a law known as Collards law, as discussed in next section. Collards law of independent migration of ions. Collards law studied that molar conductivity is at infinite dilution lambda naught m for a number of pairs of strong electrolytes, such each pair having a common cation or anion. Then he calculated the difference of these lambda naught m value for each pair. It is observed that difference between lambda naught m value for each pair of sodium and potassium salts having a common anion was same irrespective of what this ion. Similarly, the difference in the lambda naught m value for each pair salts having the same difference anion and a common cation was same irrespective of what this cation was. In fact, column 3 in table 2.1 gives the lambda naught m value of K positive ion minus the lambda naught m value for Na positive ion. Similarly, the last column gives lambda naught m value for K positive ion minus the lambda m value for Na positive. Similarly, the last column lambda naught m value for Br negative ion minus lambda naught m value for Cl negative ion. On the basis of the above observation, Collards concluded that each ion makes a definite contribution to the total molar conductivity of an electrolyte at infinite dilution, irrespective of the nature of other ion of electrolyte. This individual contribute of an ion toward the total molar conductivity of electrolyte is called molar ionic conductivity. As a result of these studies, Collards in 1876 put forward a generalization known after him as Collards law. It states as under: the limiting molar conductivity of an electrolyte at infinite dilution is the sum of the limiting ionic conductivities of cation and anion, each multiplied with the number of ions present in one formula unit of electrolyte. Lambda naught m for AXBY is equal to X lambda naught A Y positive and lambda naught B X negative, where lambda naught m is the limiting molar conductivity of electrolyte. Now, Arrhenius' theory of ionization. To explain a number of phenomena related to electrolytes such as conductance, electrolysis, anomalous behavior of electrolyte toward colligative properties, Arrhenius in 1887 put forward a theory about electrolysis. This theory is known as Arrhenius' theory of electrolysis dissociation. The main points of this theory are summarized below. An electrolyte, when dissolved in water, dissociates in positive and negative charged particles called ions. The process is called ionization. Example: NaCl gives Na positive, Cl negative. MgCl2 gives Mg2 positive plus 2Cl negative. Next, the total charge carried by the positive ion is equal to the carried by the negative ion, so that solution as a whole is electrically neutral. On electrolysis, the positive ion migrate toward cathode and hence are called cation, while the negative ion migrate toward anode are called therefore anions. The ions forms constantly renew to form the undissociated molecule, will ultimately there is an equilibrium between the ion and the undissociated molecule. Example: NaCl equilibrium, Na positive, Cl negative. In other words, the whole of the electrolyte may not dissociate into an ion. Instead, only a part of electrolyte may dissociate into ions. The degree of dissociation increase with dilution and become maximum at the infinite dilution. The conductance of an electrolyte solution is due to the ion produced by the dissociation of electrolyte. Greater the dissociation, higher is the conductance. Substances like mineral acids, alkalis, and most of the salt, which shows a high conductance, is due to the fact that they possess high degree of dissociation. Their molecules are almost completely dissociate into ions. In the aqueous solution, such substances are called strong electrolytes. On the other hand, substances like acids and bases and some of the organic acids and inorganic bases etc., which show poor conductance, is due to the fact that they possess low degree of dissociation. They are only partially dissociate in the aqueous solution. Such substances are called weak electrolytes. The ions produced by the dissociation of electrolyte behave like molecule toward colligative properties. For example, each NaCl molecule dissociate to give ions Na positive and Cl negative. Hence, the observed value of any colligative property is double than expected value. The properties of an electrolyte are the properties of its ions. For example, the properties of an acid are due to H positive ion furnished by the aqueous solution. Similarly, properties of a base are due to H negative ion produced in the aqueous solution. Oswald dilution law. According to Arrhenius theory of ionization, when an electrolyte is dissolved in water, there is an equilibrium between the ion and undissociated molecules. Oswald in 1888 pointed out that law of chemical equilibrium can be applied on the ionic equilibrium to obtain an important relationship known as Oswald dilution law. Suppose the initial concentration of binary electrolyte AB in the solution is C moles per liter and alpha is the degree of dissociation, then we will have AB equilibrium A positive plus B negative. Initial concentration is 0 0 and concentration at equilibrium C minus alpha C alpha C alpha means C bracket 1 minus alpha. Apply the law of chemical equilibrium, we get K is equal to A positive B negative divided by AB. So K is equal to C alpha square divided by 1 minus alpha. The equilibrium constant K for the equilibrium AB equilibrium A positive plus B negative is called the dissociation constant or ionization constant of the electrolyte. AB or may be represented by Kd. Like any other equilibrium constant, Kd is constant only at constant temperature. The unit of Kd will be same as those of concentration C. If the degree of dissociation alpha is very small, as is usually the case of weak electrolytes at ordinary conditions, alpha can be neglected in comparison to 1 in the denominator of expression. Then the approximate formula becomes alpha is equal to root Kd upon C. For a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is inversely proportional to the square root of initial molar concentration. Further, as concentration in the moles per liter, therefore the volume of solution containing 1 mole of electrolyte will be 1 upon C liter. Putting 1 upon C is equal to, with the expression 1 and 2 can be written as alpha is equal to root K dV, where V is the volume of solution in liter containing 1 mole of solute. Thus, Oswald's dilution law may also define as, for a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is partially proportional to the square of volume in the containing 1 mole of electrolytes. Limiting Arrhenius theory. Arrhenius theory was able to explain a number of facts and phenomena, but soon a number of objections were raised against this theory, especially when applied to strong electrolyte. A few of these objections are as follows. Arrhenius suggested that ionization of the electrolyte take place when dissolved in water. However, X-ray studies have shown that many such electrolytes are already in ionized state. Hence, the word ionization has been replaced by the word dissociation. As an electrolyte can conduct electricity even in the molten state, it shows that dissociation of electrolyte take place even in molten state. The most serious objection against the Arrhenius theory was its utter failure when applied to strong electrolyte. Example: Oswald dilution law, which is derived on the basis of Arrhenius theory using the concept of ionic equilibrium, fails the strong electrolyte. Constant value of dissociation constant K is not obtained. The degree of dissociation alpha of strong electrolyte calculated for conductance measurements was found to be different from the calculated from colligative properties. The value were found to be nearly same only for univalent electrolytes. Strong electrolytes are almost completely dissociated even at moderate concentrations. Alpha is equal to 1 or 100% at all concentration. Hence, Arrhenius' view that conductance increase with dilution because the dissociation increase does not make any sense in case of strong electrolytes. The increase in conductance with dilution must be therefore due to some other factors. Intrionic effect discussed in next section. The ratio lambda C upon lambda naught is therefore better called apparent degree of dissociation or conductance ratio only. Debye-Huckel theory. The conductance of the solution of an electrolyte depends not only upon the number of ions but also upon their speed. In case of weak electrolyte, the increase in conductance with dilution is due to increase in dissociation of electrolyte due to increase in number of ions. The speed of ion in the case are not much affected by the change in concentration because the number of ions produced is so small. Distance between them is quite large so that there is no interference in the movement of an ion or other ions. However, in case of strong electrolytes, the number of ions produced on dissociation is so large that freedom of movement of an ion is hindered by the other ion present around it. When the solution is diluted, the ionic interference decreases and hence ionic speed increases, and so does the equivalent conductance. The first successful attempt to explain the variation of equivalent conductance of strong electrolyte with the dilution qualitatively was made by Debye and Huckel. The fundamental idea underlying their work is that because of electrical attraction among the oppositely charged ions, each of ion is surrounded by a large number of oppositely charged ions, and this affects speed of ion in electric field. There are such effects which are briefly described below. The electrical attraction among the oppositely charged ion which affect the speed of an ion in the electric field is called interionic effect. Relaxation effect or asymmetric effect. In the solution, each ion is surrounded by ionic atmosphere of opposite charge so long as no electric field is applied. The ionic atmosphere remains symmetrical around the center. However, when a current is passed through the solution, the center ion move toward the oppositely charged ions. However, neither the destruction of old ionic atmosphere nor the formation of new ionic atmosphere take place instantaneously. Each of them take place time called time relaxation. Now, electrophoretic effect. When EMF is applied, the central ion moves in one direction and the oppositely charged ionic atmosphere move in opposite direction. As the ionic atmosphere moves, the solvent molecule associated with it also move along with it. Thus, the flow of the ionic atmosphere and that solvent molecule attached to it take place in direction opposite to that of movement of central ion. This effect is called electrophoretic effect since it is similar to that opposite the movement of colloidal particle in electric field. Based upon the above idea, Debye and Huckel derived a mathematical expression for the variation of equivalent conductance with concentration. This equation was further improved by Onsager and now equation is known as Debye-Huckel-Onsager equation. Lambda c is equal to lambda naught minus bracket 82.4 upon dt 1 upon 2 plus 8.20 into 10 raised to power 5 dt upon 3 into 2 lambda naught bracket root c, where lambda c equivalent conductance at concentration, lambda naught equivalent conductance at infinite dilution, d dielectric constant of medium, neta viscosity of medium, T temperature or C concentration. Migration of ions and transport number. Migration of ions. When electricity is passed through the solution of an electrolyte, the ions present in the solution are liberated at the electrodes. Electrolytes occur. This movement of ion toward the oppositively charged electrode is called migration of ions. That ions actually exist independently and move with the passage of current in solution toward the oppositely charged electrode can be seen experimentally as follows. Take a U-shaped tube, fill it lower portion by Cu2Cr2O7 jelly obtained by mixing a 5% solution of agar-agar and mixture of CuSO4 and K2Cr2O7 and allow it to set. The jelly is green in color. To mark the position of jelly, some charcoal is scattered over the green jelly. Over charcoal in both the limbs is added KNO3 solution in agar-agar KNO3 jelly and the aqueous solution KNO3. When current is passed, blue colored CO2 positive ion are seen moving toward negative electrode and yellow colored Cr2O7 2 negative ion are seen moving toward positive electrode. After some time, the two type of ions are seen moving with well-defined boundaries. The experimentally clearly are migration of ions. Migration velocity of ions and change in concentration heat of theoretical devices. According to Faraday's second law of electrolysis, when the same quantity of electricity is passed through the solution of different electrolyte, the ions are always liberated in equivalent amount. This, however, does not necessarily mean that ion moves with same speed. It may be illustrated as: consider a cell containing the solution and provided with the anode A and the cathode C. Let the solution lying between the electrode A and C be divided into three compartments: the anodic, middle and cathodic, with the help of imaginary pores, partitions A and C shown by dotted line. Before electrolysis, suppose that there is 13 pair of ions, positive signing indicate cation and negative is indicated anion, 4 being present in each of the anodic and cathodic compartment and 5 in the middle. Now the following different cases may be considered. Case 1, when only anion move. Let 2 anion leave cathodic compartment and enter anodic compartment. We get the position 2. Although the cation have not moved, still we see that the number of ions liberated is same at both the electrode, but we see that concentration in anodic character anodic chamber has not altered, while that is cathodic chamber has fallen 2 molecules. Similarly, we can show that if cation are capable of movement and 2 of them enter cathodic compartment from anodic compartment, there will be a fall in concentration of 2 molecules in anodic chamber. Thus, we see that velocity of an ion is proportional to the fall in concentration of chamber from where it leaves. Case 2, when cation and anion move at the same rate. Let us assume that two cations move from anodic compartment to the cathodic compartment and two anions move from the cathodic compartment to anodic compartment. Then we get position 3. In this case, there is a fall in concentration of 2 molecules in each compartment, but as we find that number of ions liberated at both electrodes is same. Case 3. When cation positive move at the double the speed of anion. Suppose that two cation from anodic compartment leave and enter the cathodic compartment. Since the speed of anion is half the speed of cation, therefore only one anion enter the anodic compartment. The position is shown fourth. We also observe that fall in concentration anodic compartment are 2 and 1 molecule respectively. Case 4. When the electrodes are attackable, the above relationship has been derived as assumption that ions do not react with the electrode, but in a silver voltmeter, each NO3 negative ion reaches the anodic compartment, react with Ag of the electrode forming AgNO3, and instead of decrease in increase of concentration in anodic compartment. This increase in concentration takes place even when Ag positive ion migrate from anodic compartment to the cathodic compartment. In order to find the increase in concentration that would have been taken place if no Ag positive ion had migrated from the anodic compartment to cathodic compartment, a silver or copper voltmeter is placed in series. Suppose the number of gram equivalent of Ag or Cu deposit in this voltmeter is X. Obviously, X gram equivalent would have been the increase in concentration of anodic compartment if no Ag positive ion had migrated from the compartment. Fall in concentration in anodic compartment due to migration of Ag positive ion is equal to X minus Y gram equivalent. Fall in concentration around cathode is equal to increase in concentration around anode is equal to Y gram equivalent. Thus, the speed ratio in the case will be given by speed of Ag positive ion divided by speed of NO3 negative ion is equal to X minus Y divided by Y. Now transport number. When an electric current is passed through the ions migrated toward the electrodes, thus the electric current is carried by ion. Each ion carries a definite fraction of the total current depending upon its speed. The fraction of total current carried by ion is called transport number or transference number or Hittorf's number. Greater the speed of ion, greater the amount of current it will carry with it, and hence greater will be its transport number. Let U and UC be the speed of anion and cation respectively. Current carried by anion is equal to UA, directly proportional to UA, and carried by cation is directly proportional to UC. So KUA is equal to KUC respectively, since current is carried only by ions. So total current carried is equal to current carried by anion plus current carried by cation is equal to KUA plus KUC is equal to K bracket UA plus UC. Transport number of anion T negative is equal to KUA divided by KUA plus UC. Similarly, transport number of cation will be T positive is equal to UC divided by UA plus UC. Now determination of transport number. There are a number of methods of determination of transport number. Hittorf's method principle that the method is based upon the principle that the fall in concentration around an electrode is proportional to the speed of ion moving away from it. Fall in concentration around cathode divided by anode is equal to speed of anion divided by cation is equal to UA upon UC. Adding 1 to 1 both sides, we get fall in concentration around cathode divided by anode plus 1 is equal to UA upon UC plus 1. So fall in concentration around anode divided by total fall in concentration both the electrode is equal to UC by UA plus UC is equal to NC. Now calculation. This method of calculation may be illustrated by taking example of AgNO3 as the electrolyte by using silver voltmeter in series. Case 1. When the electrodes are attacked when the platinum electrode are used. After electrolysis, suppose weight of anodic solution taken out is equal to W 1 gram. Weight of AgNO3 found to be present is equal to W 2 gram. So weight of water present is equal to W1 minus W2 gram. Thus W1 minus W2 gram of water contain W2 gram of AgNO3 after electrolysis. In term of gram equivalent, W2 gram of AgNO3 is equal to W2 upon 170 gram equivalent of AgNO3 is equal to W2 upon 170 gram equivalent of Ag is equal to X gram equivalent. Hence we can say that after electrolysis W1 minus W2 gram of water contain X gram of equivalent of Ag. Before electrolysis, post W3 of solution contain W4 gram of AgNO3. So weight of water present is equal to W3 minus W4 gram. Thus W3 minus W4 gram water contain W4 of AgNO3 before electrolysis. W1 minus W2 gram of water will contain is equal to W4 upon W3 minus W4 into W1 minus W2 gram of AgNO3. So this is equal to Y gram equivalent. When the electrode are not attackable, X is less than Y. So fall in concentration of anodic compartment Y minus X gram equivalent of Ag. Suppose the weight of silver deposit in the silver voltmeter is equal to W gram is equal to W upon 108 gram equivalent of Ag is equal to Z gram equivalent. So transport number of Ag positive and T Ag positive fall in concentration of around anode in equivalent divided by voltmeter in gram equivalent. So Y minus X upon Z. Transport number of NO3 negative ion is equal to 1 minus T Ag positive. Case 2. When the electrodes are attracted, in the case of NO3 negative and reaching the anode attack the silver anode, there is increase in the concentration of Ag positive ion in the anodic solution. In this case we will have X greater than Y. So increase in concentration of anodic solution X minus Y gram equivalent of Ag. This increase in concentration of take place in spite of migration of Ag positive ion from the anodic compartment of cathodic compartment. If no Ag positive ion had migrated from the anodic compartment, the increase in concentration of Ag positive ion in anodic compartment would have been higher and equal to Z equivalent of Ag. Hence, fall in concentration in anodic solution due to migration of Ag positive ion is equal to Z minus X minus Y gram equivalent of Ag. So transport number of Ag positive ion is equal to Z minus X minus Y upon Z. Transport number of NO3 negative ion is equal to 1 minus Tag positive. In case of copper voltmeter is used, the number of gram equivalent of copper deposit in voltmeter is obtained by dividing the weight of copper deposit by its equivalent weight.